Okay, so in this video in fluid statics, we'll talk about pressure distribution with height. To start with, in fluid statics, we're basically talking about a fluid where there is no tangential or shear forces, and therefore there is no continuum, there's no continuous deformation of the fluid. And of course, this can only occur if the fluid is at rest or if it is moving as a rigid body, so that all the particles in the fluid have the exact same velocity. So under these circumstances, we want to look at the equilibrium of this fluid, and for that there is two relevant forces that might appear, which are pressure and gravity. And of course, in more complex situations, you might have electromagnetic forces and so on, but these we will not consider in this course. And the goal now is to find the relation between these forces so that we can relate or get an expression for the fluid pressure. So for that, I will consider this fluid region, and from it we will carve a little cube that we will term an infinitesimal element. So this will have dimensions dx, dy, and dz. And of course, although we're plotting it here quite big, we have to imagine that this is really a tiny part of the fluid. We will need from it the volume, which is simply the volume of a cube. So dv is equal to dx, dy, dz. And then also, if, for example, we look at the area of this face here, we'll have dA equal dx times dz. And of course, we can do the same for all the other faces. So with that, we can look at the force of gravity. So basically, we call it dFg, a d again because it's a force acting on an infinitesimal element, and therefore is also an infinitesimal force. And this force, well, gravity, is simply mass times acceleration being a vector, and the mass we can write as density times volume, and the volume we saw before, it was just dx, dy, and dz. And of course here, because the element is so small, we can consider the density as constant even in a compressible fluid. So with that, we can move to pressure. We'll consider the pressure at the center to be P. We first need to compute or estimate the pressure at the right and at the left, because pressure is not going to be constant. That's exactly the variation we want to look at. So if we imagine that pressure in x direction varies in an unknown manner, and this is our central point with pressure P, this is our right point with pressure P right, and we have here this distance will be dx over 2, because it's half of the element. And a first way to approximate is just to have a straight line here, and therefore if it has a slope s, we would simply have that P right is equal to P plus s times dx over 2. And now this s, what can it be? Well, if this is close enough, this line would be equal to the tangent line at P, so to the derivative. So therefore we can write P right is equal to P plus the derivative of P with respect to x, dx halves. And then the same we can write for P left will be equal to P, and now minus dp dx and dx halves. And so with that, we have the pressure at each end, so we can go and compute the forces. So if we look at the Fp on the right, let me only write the substitute out, that would be the pressure on the right times the area. So the pressure will be P plus dp dx halves times the area. And the same we can do for the pressure force at the left will be P left, the area, so equal to P minus dP dx halves the area. And so, of course, the total force on x direction will be P left, will be dFP left minus dFP right, where of course the right one is with a minus sign because it's pointing towards the left, and the x is defined positive towards the right. So if we combine, we will have P left first, so P minus dP dx halves times the area minus P plus dP dx halves, and the area in here. And now we can see that this P and this P cancel. This minus will turn into a minus, so we will have minus dP dx halves minus dP dx halves times the area. So in the end, we'll have minus dP dx times dx, the area. And finally, the area was dP dx dy and dz. And remember that this was dV. And I forgot a minus sign here. So good, that was the force in x direction. Of course, we might have pressure in y and z direction as well. And let me just recap. So we have the Fp on x direction was minus dP dx dV. And I'm not going to derive it again, but you can see it's exactly the same. We can do the same for y and for z. So for y is dP dy dV, and for z is equal to dP dz dV. What we can do is write this as a vector. So the Fp will be minus, now dP dx, the x component in the vector I, which is the vector going in x direction, plus dP dy times j, plus dP dz times k, and all with dV. And this operation, it's what we call the gradient, and it's quite often written as the Navla operation, so Navla P, or the gradient of P, times dV. And with that, we already have the force of pressure. So finally, we can combine and put everything together. So basically, remember we had the sum of forces, and this is on this infinitesimal element, will be equal to what? The force of gravity, Fg, plus the force of pressure. The force of gravity was rho times g as a vector, and the force of pressure was minus the gradient of P. And I missed the dV's in both sides. And then, of course, if we're in equilibrium, the sum of forces must be equal to 0, so we get our equation. Now we can cancel the volume, and we get the basic equation of fluid statics, which is rho times g is equal to Navla P. That, if you're not comfortable with Navla, we can write in Cartesian coordinates. And we can assume that gravity is going in the negative z direction, so it's pointing downwards. And then we would have that dP dx is equal to 0, that dP dy is equal to 0, and that dP dz is equal to minus rho g. So basically, this thing is telling that this constant in horizontal direction, so in x and y direction, or in more generally, is constant perpendicular to the gravity. And this one we can write now, if it only depends on z, the partial derivatives can be written as normal derivatives. So this we can write as dp equals to minus rho g dz. So this is basically telling us that the pressure is increasing as z decreases, so as the depth increases. So with that, we can look at an incompressible fluid and see how pressure will vary in there. So we have this plane here at height z0 and pressure p0. That's a reference plane. That's somewhere where we know the pressure. And of course, it can be a plane because there's no variation in x and y. So now what we want to look is, say, we have now a point here z at a certain depth, and it will have a pressure P. And we want to know what the pressure is. So we can start from the fundamental equation, written like this: dP equals minus rho g dz. And this equation we can simply integrate from our reference pressure from our reference state, which is P0, to our pressure P, and here the same from our reference state Z0 and to Z. Now, dP is just a constant, so the integration is simply P minus P0, and here rho and G are also constants, because we're assuming the fluid is incompressible, so here we have rho G and then Z minus Z0. So more generally, more concisely, we can write that the change in pressure is equal to minus rho G times the change in height. Where this minus, remember, that means that as we go down, the pressure increases. However, the previous one was only valid in the case of an incompressible fluid. So now let's consider a compressible fluid. Let's take an example of an ideal gas, where the pressure, the density can be written as P over RT. So in this case, the basic equation is still true. We still have minus rho G dz. However, now rho is P over RT dz. So in order to integrate this, we can move P to the other side, and we'll have dP over P is equal to minus dz over RT. And again, we can integrate from the reference pressure to our pressure and from the reference height to our height. We integrate that, here we will get a logarithm. So we get logarithm of P divided by P0. And here, this is a constant, so we will simply have Z minus Z0, or with a minus in front, over RT. Now we can expand the logarithm and find P equal P0 e to the minus change of height over RT. Now we get a fairly more complex equation. And that would be all about pressure variation.